Hello everyone, my name is Mehdi Noor, and in this video I will be giving you guys a basic introduction to the topic of vector calculus. Now, this is a very important topic. It's integral in differential geometry, in physics, in engineering, among many other things. Now, before we delve into the calculus aspect of this topic, let's first discuss some of the more basic things that we need to know first. So let's start off with vectors. So what are vectors? These are just quantities that have both a magnitude as well as a direction, right? So we can just use vectors to describe quantities that have both a magnitude as well as a direction, right? This is the most basic definition of a vector. So let's consider some point A and another point B. Let's imagine that we have a particle that is traveling from my initial point A to the terminal point B along this line segment, right? And it's doing so in this particular direction. Then this will correspond to a vector. And in this specific case, it will correspond to a displacement vector. So we can denote a vector with an arrow on top. And this is corresponding to a displacement vector. So what is a displacement vector? This is just the shortest distance between 2 points, between my initial point and the final point. That is my displacement vector. Right, and the length of this arrow, the length of this vector, represents the magnitude. And the arrow that is pointing towards gives us the direction of the vector. So if I were to have another vector that is completely parallel to this initial vector, that also has the same exact magnitude, let's say it's from C to D, if let's say this is the vector A, right? If this vector and this vector have the same magnitude and the same direction, then we can say that these are both equivalent vectors. They are the same vector, right? We can also have a zero vector, which is denoted by 0, meaning this has a magnitude of 0 and it doesn't have any specific direction. Right, now it is very useful to be able to treat vectors algebraically. So let's introduce a two-dimensional coordinate system like this. So we have our coordinate axes x and y, and the point of intersection of these axes is my origin. Let's place the initial point of a vector at the origin and the terminal point somewhere here of the vector. Let's say this is the vector u, and this point has the coordinates u1 and u2. So my x coordinate is u1 and my y coordinate is u2. Similarly, I can do the same thing for a three-dimensional coordinate system. So if we consider a three-dimensional coordinate system like this, so this will be my x, y, and z axes, and our origin is here. Similarly, let's consider a vector from this point to another point here, and this will have the coordinates. So if I denote the vector here by a, this will have the coordinates a1, a2, and a3, right? And we can find these coordinates by just considering the projection of this vector onto my xy plane first. And from this, we can find my y coordinate to be a2, my x coordinate to be a1, and if I project this onto my z-axis, this will be a3, right? And these coordinates, these are just the components of my vector. So this is the component, these are the components of vector u, these are the components of my vector a, right? And if I were to find the magnitude of this vector, if I wanted to find the magnitude, then how could I do this? Well, I can just consider the absolute value or the modulus of this vector. So I can just consider the modulus. This will be equal to the square root of the sum of the squares of these individual x, y, and z components, right? So for the vector a, my x component is a1, my y component is a2, and a3 is my z component. So I will have a1 squared plus a2 squared plus a3 squared. And this gives me the magnitude of the vector a, right? And if I were to do the same thing for u, this will be just equal to u1 squared plus u2 squared, right? This is the magnitude of my vector u. This is the magnitude of vector a, right? Now we can also represent a vector as well as its components in 3 dimensions as follows. Let's say that I have a vector A like this. I can express this vector in terms of its as well as its components in terms of some basis vectors. So I can write this as AXI plus AYJ plus AZK, right? Here AX is my X component of the vector, AY is my Y component, AZ is my Z component, right? And what is I, what is J, and what is K? These are my standard basis vectors. So these are just my basis vectors, right? So now what are basis vectors? Well, these are just vectors that are pointing along my coordinate axes. So let's consider a 3-dimensional coordinate system again. This is X. So let me draw this again. So let me consider a 3-dimensional coordinate system again. This is my X coordinate, sorry, my X axis, my Y axis, and Z axis. So my I basis vector, this will be pointing along my X axis. So this will be along my X axis. The J basis vector will be pointing along my Y axis, and my K basis vector will be pointing along the Z axis. And these basis vectors are also unit vectors, right? These basis vectors are also unit vectors, right? These are just vectors that have a magnitude of a single unit. They have a magnitude of 1 unit, right? So if I were to consider my basis vector I from the origin to some point, then this will have the coordinates 1, 0, 0. For my J basis vector, this will have the coordinates 0, 1, 0, and this will have the coordinates 0, 0, 1, right? So my basis vectors are just pointing along my X, Y, and Z axes respectively, right? So we can just express any vector, whether it's in 2 dimensions or in 3 dimensions, as well as its components in terms of these unit vectors, right? So let's say that I actually have a vector. So let me just get rid of all of this. Let's say that from my origin, I have some vector A. So this is my vector A. And I want to find a unit vector. I want to find a unit vector that is in the direction of my vector A, right? What does that mean? I just want to find a unit vector that is pointing in the same direction as this vector, right? So along this direction. So how can I do this? To find that unit vector, let's represent the unit vector with this. So to do this, I can just consider my vector A divided by the magnitude of A, right? The magnitude of A will just be the square root of AX squared plus AY squared plus AZ squared, right? So this will be just equal to this, right? And this will give us my unit vector. And this unit vector will just have a length or a magnitude of 1. So this will be my unit vector of magnitude 1 that is pointing in the same direction as the vector that is given here. Okay, so now let's consider a vector A. Again, let's consider some vector A. And let's say that this time this vector is some function of a variable t, of some scalar variable t. So what is a scalar? A scalar is just a quantity that only has a magnitude. Just a quantity with only a magnitude. It has no direction. So we can just describe a scalar quantity with a single element or just a number, right? So here we're considering our vector to be a function of some scalar variable t, right? So now we have a vector function, right? So we have a of t, and we can express this as ax of t, I plus ay of t, j plus az of t, k, right? So these are my x, y, and z components. And you can see that these scalar quantities are also functions of t. These are also just functions of t, right? And if I were to differentiate, so if I were to find the first derivative of this vector with respect to t, so if I were to find the first derivative, then to do this, I will just have to consider the first derivatives of the individual components, so the x, y, and z components of my vector function a, right? So I will just be taking the first derivative of my vector components. So I will have dAx by dt I plus dAy by dt j plus dA, so dAz by dt k, right? So as you can see, my x, y, and z components for the derivative are actually just the derivatives of my x, y, and z components of my original vector function that I had, right? And this derivative is itself also a vector. So this is also a vector itself. The derivative of this vector function also gives us a vector, right? So let's consider an example. Let's say that once again on a Cartesian three-dimensional coordinate system, x, y, and z, let's say that we have a curve. Let's say we have some curve like this. We have a curve C, and we are considering a particle that is traveling along this curve over a period of time, right? And for a specific moment in time, for a specific time t, our particle is at a certain position here. Let's say this is the point P, and it has the coordinates x, y, and z, right? So at a specific time, our particle is at this point on the curve, which has the coordinates x, y, and z, right? And we should always specify the position of a particle with respect to a certain reference frame by some displacement vector. So we can specify this position with respect to this reference frame, so our Cartesian coordinate system, by some displacement vector. So from our origin up to this point, we have some displacement vector. Let's say this is r of t. So our displacement vector is a function of time, right? As time progresses, the particle will be at a different point, and we will have a different position vector, right? So our displacement vector is a function of time. So we can express this vector like this. We have I rx plus j ry plus k rz, where these are my x, y, and z components, right? So this is my displacement or position vector. Displacement or position vector. And if I were to take the first derivative of this vector function, I will get my velocity vector, right? So if I were to find, so the velocity vector is defined as the first derivative of my displacement vector, and this will give me I drx by dt plus j dry dt plus k drz by dt, right? Where these components, these are my components of the velocity vector. This is vx, this is my vy, this is vz, right? So this is my velocity vector, and I can also write this as r dot, right? If I'm taking the derivative of something with respect to time, if I'm taking the derivative of a vector with respect to time specifically, I can denote that with a dot on top. So this means that this is the derivative of r with respect to time, right? So if I take the derivative of the velocity vector, I will get my acceleration vector. So I will get a to be equal to the derivative of the velocity vector with respect to time, which is also equivalent to the second derivative of my displacement vector, which is r double dot meaning second derivative with respect to time. So this will be equal to I dvx by dt plus j dvy by dt plus k dvz by dt, right? So this is my acceleration vector. So the velocity vector, this gives us the rate of change of the position of our particle, right? And our acceleration vector, this gives us the rate of change of the velocity of our particle, right? So, for example, let's consider a particle. Let's consider the position vector of a particle at some specific time t in Cartesian coordinates to have a displacement vector like this. This will be equal to 2t squared I plus 3t minus 2 j plus 3t squared minus 1k, right? So this is my displacement vector. I can just find the velocity vector by considering the first derivative, which is 4t plus 3i plus 6tk, right? And to find the acceleration vector, I will take the derivative of the velocity vector with respect to time, and that will give me 4i plus 6k. This becomes 0, right? So this is my acceleration vector for this specific case. And if I wanted to find the speed of the particle at a specific time, let's say at t is equal to 1, I want to find the speed of the particle. Well, to do so, I can just consider my velocity at t is equal to 1. That will give me 4i plus 3j plus 6k. And to find the speed, I will just consider the magnitude, right? The modulus of the vector, which will be 4 squared plus 3 squared plus 6 squared, and that will give me root 61, and this will be my speed. All right, so let's take a look at some differentiation rules for finding the derivatives of some vector functions. Let's say that I have a vector function a and b, and let's say that these are both functions of some scalar quantity s, for example, right? So these are both vector functions. If I were to find the derivative of the sum of a and b with respect to s, then this is just going to be equal to the derivative of a with respect to s plus derivative of b with respect to s, right? And let's say I have some scalar quantity c. This is some scalar quantity. If I multiply a vector, so let's say the vector a is represented like this. If I multiply this vector by some scalar quantity, let's say if I multiply it by 2, right, then the resulting vector will be a vector that is in the same direction but with twice the magnitude, with twice the size or length, right? So if I multiply a vector a with some scalar quantity c, then the derivative of this is just going to be equal to c times the derivative of a with respect to s, right? And we should already be familiar with the dot product or the scalar product, right? So if I have the dot product of two vectors like this is just equal to, so we have a xi, a yj plus a zk. We have b xi plus b yj plus b zk, right? So if I take the dot product of these two vectors, then I will get something like this. We will have ax bx plus a y by plus a z bz, right? All we did was multiply my x components, sum it with the multiplication of the y components and then the z components, right? And the resulting thing that we get is something that is completely scalar. We just get a scalar quantity, not a vector. So if I were to take the derivative with respect to s of the scalar product of these two vector functions, well, this is just equal to the derivative of a, so the dot product of the derivative of a with b plus the dot product of the vector a with the derivative of b with respect to s, right? And finally, let's move on to the vector product. So we've looked at the scalar product. Let's now look at the vector product. So the cross product of two vector functions. So if I find the vector product of a and b, well, first thing I can do is I can express this or I can just write this in the form of a determinant. So in the first row, I have I, j, k, my basis vectors. The second row, I have the components of ax, components of the vector a. So I have ax, ay, az. And in the third row, we have the components of b. So I have bx, by, and bz. right? And without going into explicit detail, we should already know that this is just equal to I times AY times BZ minus AZ times BY. We have AY, BZ minus AZ, BY. And then when I consider J, I have AX, BZ minus AZ, BX. And finally for K, I have AX, BY minus AY, BX, right? So this is equal to the vector product of A and B. And if I were to take the derivative of the vector product of A and B with respect to S, then this is just equal to the cross product of, or the vector product of A with the derivative of B plus the vector product of the derivative of A with B, right? And the resulting thing that we get is itself also a vector. So this is also a vector, right? And this will be a vector that is perpendicular to both the vectors A and B. So it will be orthogonal to A and B. So we can also write this in determinant form. So we have the basis vectors again, I, J, K. Second row, we have the components of A. And in the third row, we have the derivatives of the components of B. So we have dBx by ds, dBy by ds, dBz by ds. And similarly, we have I, J, K for this term here. We have dax by ds, day ds, daz by ds. And then we just have the components of B, right? So this is equal to the derivative of the vector product of A and B.